Hello, everyone. Thank you for giving us this Test of Time award. It's a great honor, and we're very humbled to receive this award 10 years after our paper's publication. Unfortunately, we are unable to attend in person at DSN. ISCA and DSN, two major conferences that we normally attend, are happening at the same time, and we had to organize some workshops over here. We wish we could be there. I will first make a quick couple of comments about this paper and how it kind of happened. And then Professor Moin Qureshi will present a quick overview of the work and its importance and impact. First, this paper was enabled by building real experimental infrastructure using FPGAs to understand DRAM chips. My group has been working on building such infrastructures to understand different behavior that happens in memory chips as technology scales to small technology nodes. And this infrastructure has enabled to understand major phenomena in DRAM, like what we describe in this paper, retention times, variable retention time, and RowHammer. And I believe this work is one of the examples of what building such sophisticated infrastructure to understand important characteristics of memory chips can enable. I would encourage everyone to build such infrastructures, however complicated they may be, to understand and validate what they're doing, if possible, even if it's a lot of work. My students did a lot of work to enable this work, and I'm very grateful for that. Second and last, this work was a nice collaboration between my group and Moin's group. We especially provided the experimental data that enabled us to build nice and simple models, which in turn enabled solutions that Moin described to an important problem. I would again encourage everyone to perform such fruitful and harmonious collaborations, exploiting and enhancing complementary strengths of different groups and people. I believe we need more of that harmony in our research. Now I will turn to Professor Moin Qureshi, who will describe the work. Thank you.
Thank you, Onur. Again, thanks to the committee for the award. The problem that we were looking at that time was DRAM refresh. DRAM capacities were increasing, and more time of the system and energy of the system was going into refresh. And at that time, there were several works that said, oh, look, we can exploit the non-uniformity in retention time of DRAM to do multi-rate refresh. Some cells are strong, most cells are strong, they don't need 64 millisecond refresh. And some cells are weak, they do need 64 millisecond refresh. So characterize the rows and do most of the rows at 4x to 8x lower refresh. And this can save a lot of power and performance. While this is a very good idea, the problem is that the retention time is not constant. It can change over time, especially for a very small set of cells. We observe that the retention time can go from high to low. And this can happen erratically, like in a manner that if it's not addressed, it can break multi-rate refresh. So at that point, multi-rate refresh was considered a theoretical idea that cannot really be deployed in real systems reliably. To understand the behavior of VRT cells, Onur's group's DRAM infrastructure was very helpful. Right? They characterize DRAM chips from several vendors, and we use that to understand how the pool of weak cells change over time. And the pool actually increases. Based on the experimental data, we developed a model for understanding VRT. And based on this model, we got a very good insight that the rate of increase in weak cells is fairly small. What if we could detect weak cells at runtime? Then we can dynamically change the rate of refresh. And how do we detect it? Server systems have ECC. If you get an ECC error, that is one indication that the error could have happened because a strong cell became a weak cell. So fix it using ECC, but also upgrade the row from using slower refresh to faster refresh. And we showed that Avatar maintains reliability and retains most of the performance and energy efficiency benefit of multi-rate refresh. This was an example of a synergistic work, right? This was the first work to show that reliable and efficient DRAM refresh was possible. This was also an example of having two different uncoordinated reliability mechanisms, ECC and refresh. Operating independently was not as useful, but if you can coordinate it, then you can get a much better solution. And this principle applies in a lot of situations. Fast forward, moving 10 years, refresh problems has actually gotten much worse. Our systems now refresh at 32 millisecond. DRAM reliability has worsened. DRAM chips now offer on-die ECC, and there is some evidence that DRAM vendors are actually using on-die ECC to optimize refresh. So some of those ideas have seeded in current DRAM chips. DRAM reliability continues to degrade. There are new failure modes such as RowHammer coming, and our insight of coordinating it with ECC is applicable to efficiently solving such emerging problems also. More broadly, modern systems are limited by memory capacity and memory bandwidth. Even if you look at AI models are constrained by memory capacity and memory bandwidth. Our ability to scale to smaller nodes will be key in getting higher capacity, higher bandwidth memories. And the biggest challenge to scaling to smaller nodes will be reliability. So the solutions that will come out at communities such as DSN would be really helpful. I'm very excited about the kind of challenges and opportunities that lie ahead.